Alright, so a lot of time in science, you really need to know multiple different things, and there's overlap between them. I've broken this unit up into 3 different sections so that you don't have to memorize a whole bunch of information and be tested over the whole thing. So, most of this PowerPoint is going to include things from the other 2 units. So, modern atomic theory and the electron. So, we have Dalton's model. He thought of atoms as being small spheres. So, tiny indestructible particles with no internal structure. J.J. Thomson discovered the electron, which led to the plum pudding model. He pictures electrons embedded in the sphere, and the sphere had a positive electrical charge. So the positive charge was spread throughout the sphere with electrons scattered in it. So we had small particles that were negatively charged. We're not going to worry about Hantaro Nagaoka. I have no clue how to pronounce his name. He did theorize about the nucleus and that electrons orbited. But it wasn't until 1911 that Ernest Rutherford actually found that the atom had a nucleus, a very small, dense, positively charged center. And then also theorized that electrons moved around the nucleus. We then get to Bohr's model. Bohr's model is where the electron moves around in circular orbits. They're at fixed distances. These orbits correspond to energy levels. An energy level thus corresponded to a certain distance away. I don't think I have Louis de Broglie and the test, but he's an important person in the atomic model. He suggested that electrons move like waves. What separated him from Erwin Schrödinger is that de Broglie, he thought the electron still existed as a particle, it just moved in a wave-like manner. So the electron exists as a fundamental particle. It has a size and a location, but it just moved like a wave. And by doing a whole bunch of math, he found an interesting property that the electrons would only orbit at a certain distance so that the wave completed itself. So if we have a nucleus, he found that an electron would move in a wave, and this is a horrible wave, but he found out that the distance that an electron would be away from the atom would do so that this path meets back up in the correct spot. So if we have it go around in a circle, we see a wave like this. When it goes around this whole circle, it'll meet back up so that it will continue this pattern. So it will complete like this and meet back up perfectly. Well, so in the mathematics, he found out that the energy level is such that it makes a complete wave. So if you've never, again, we'll go back into waves in another unit. But this is a wave. if we look at one portion of it, this would be a complete wave from here to here. Also, this would be a complete wave from one spot to another. So if we were to continue it, this is basically two waves. This, however, would be half a wave. So they would not go around the atom so that we ended up something like that. This would be wrong. But you just found out that they have to make full waves. They have to connect in the correct spot on each other. As I told you, the Bohr model is not the correct model that describes the atom. However, despite it being wrong, it was useful in the advancement of atomic theory. By using the Bohr model, he found this coincidence that electrons can be thought of as waves. He didn't realize, though, that the electron doesn't really exist as a particle when it's not being observed. He thought that it was still a electron. It just had a wave-like motion. Then comes Erwin Schrödinger. He developed a mathematical equation to describe the motion of electrons, which led to the electron cloud model. In it, we no longer have electrons in definite spots moving in definite orbits. We instead have this electron cloud. And all the cloud is the probable locations of finding an electron. The more dense the cloud is, the greater the probability of finding an electron in it. So the electron becomes a cloud of probability, of probable locations you'd find it. This wasn't mentioned in the other PowerPoint, but it is on the test. So we now have electrons. We now have energy levels. We now have a nucleus. From the nucleus, we can derive the proton. And what else is in the atom but the neutron? James Chadwick was an English physicist that discovered the neutron. And so atomic nuclei contain both neutrons and positively charged protons, was James Chadwick. So we discovered the electron with J.J. Thomson by running electricity through a neutral gas and noticing negatively charged particles come off. James Chadwick discovered that the same atoms have different mass. He basically discovered the isotope. So he took, bless you, he took and tried calculating the mass of atoms, and he would notice like 2 atoms of gold or 2 atoms of carbon have different masses, but they were both still the same type of atom. He concluded that there had to be some neutral particle that allowed them to have different masses, but because it was neutral, it did nothing to the atom's nature. So the Bohr model, introduced by Niels Bohr, most of all this work is just done on hydrogen because it's extremely advanced and difficult to work on higher atoms. But for hydrogen, he proposed that an electron is found only in specific circular paths or orbits. Again, the Bohr model is wrong. They don't actually orbit, but we still call them orbits. We still call these orbits, even though they're no longer considered to be orbiting our circular paths. So we have something known as the ground state and the excited state. The ground state is when an electron is in the lowest possible energy level, also call it an orbit. And its excited state is when an electron jumps up to a higher energy level or orbit. So here are two orbits of hydrogen, and because it only has one electron, it would be considered in the ground state. So the electron cannot fall any lower because it's at the lowest orbital. For larger atoms that have multiple electrons, we'll see later that each orbital can only hold at most, depending on what you mean by orbital. There's only each orbital, each energy level, I should say, and this is really energy levels. Let me actually just scratch out these words, orbits. We'll learn a little bit that there's a distinction between energy level. An energy level can have multiple orbits. Here we have two energy levels. We can find out that a certain energy level can only hold so many electrons. So this lowest one can only hold 2. So if we had 3 electrons, there would be in the ground state. So for example, lithium, right? Yeah. So for example, lithium has 3 protons. Four neutrons and 3 electrons. The lowest energy level can only hold 2 electrons. So for so this is lithium nucleus. Energy level 1, we have 2 electrons. And here we have this one N2, so energy level 2. And this would be energy level 1. This would also be in the ground state. So ground state doesn't mean that all the electrons in their lowest energy, it's lowest possible energy level. So this electron can't jump down because this inner one can only hold at most 2. We'll look at orbitals and energy levels in the next portion. I'm splitting it up, but it's still important to understand this concept now. Whenever we have, so going back to hydrogen, with a single proton, only other protons, gold. So what happens is, it jumps up to a higher energy level. This would be known as excited. The electron absorbs some energy and goes into a higher energy level. Oh, you're right. Ground state, because electrons cannot be in any lower energy configuration. And these are Bohr's models, by the way. We'll be using it when we go into describing. It's very useful in actually listing all this out. Everyone good? So each electron has a fixed energy. This fixed energy is its energy level. Electrons can jump from one energy level to another, but electrons cannot be or exist between the energy levels. So you will never find an electron halfway between two energy levels. It's either at one energy level or it's at the other energy level. A quantum of energy is the amount of energy needed to move an electron from one energy level to another energy level. This is where the word quantum comes in quantum mechanics. I've lost the internet. Quantum is just a specific amount. The opposite of a quantum would be continuous. So a quantum is a discrete amount, meaning that the energy levels can't be any specific number. There will be multiples of some other number. So as for example, like the real numbers versus the whole numbers. So whole numbers are 1, 2, 3, 4, 5, so on. Whereas real numbers is like 1.5, pi, 2/3, and such like that. Quantum just simply means that there's a certain fixed amount of energy. It's discrete or quantized. When we go over waves, we'll look at this more in detail. But what happens is, so energy is conserved in the universe. What causes an electron to go from one state to another, or one energy level to another, is whether or not it absorbs a photon. Photon is just a particle of light. So light can also be thought of as a wave or a particle. And what this means is if an electron is in a high energy level and it falls down to a low, it has to give off energy. It gives off energy in the form of electromagnetic waves or light. Whenever to get an electron to go from a low energy to a high energy, it has to absorb some light. Did y'all know that y'all are all glowing right now? What color are y'all glowing in? So if you were to stand in a pitch black room, you'd be giving off white light? Can y'all think of any sort of camera that even if you turn out all the lights would still be able to detect you? Thermal camera? So what type of EM wave is thermal light? Close. Infrared. So around this temperature, the atoms and electrons are constantly moving in such a right way that they're giving off infrared radiation. So if you had a camera that can see in infrared, you'd be able to see people glow. We give off infrared radiation. If you were to continue heat up and cause the atoms to be moving faster and faster, they'll start giving off more visible light. So, for example, the iron bars in your oven, if you have an electric oven, it begins glowing in infrared, which we can't see. As you heat it up, they'll start becoming a very dark red. And as you continue to heat up, they'll start glowing more red, and then orange, then yellow, and eventually starts glowing in all the visible colors and become white hot. We'll go over this later when we deal with waves. We'll actually go see. I have some gas in a glass tube, and I can run electricity through it, which will produce energy, causing the electrons to jump up, and it's unstable. Everything wants to be in the lowest energy configuration. Electrons do not want to be at higher energies. It's unstable. They'll eventually fall back down. So if I run electricity through a gas of just one element, all the electrons will bounce up and then fall down, releasing a photon. Electrons can also jump from energies not just by absorbing light. Running electricity through them is another way. Also, heat. Heat can any way you can transfer energy to it. But whenever they fall down, they usually always give off photons. So to move from one level to another, electron must gain or lose just the right amount of energy. So it'll always give off the same frequency of light. Gain energy to move to higher levels or away from the nucleus, and to lose energy to move to lower levels, closer to the nucleus. So we'll be basically doing this experiment, looking at the different colors of light. This is mostly, though, all going to be on the wave section when we go over waves. Bohr's model. So quantum mechanics. They treated electron as if it was a true wave. This is the Schrodinger equation on the bottom. By the way, the psi is a function, but the h and the e are actually operators, meaning that they're like a plus sign and a minus sign. They're not just being multiplied. So let's see. So in the quantum mechanical model, also known as the wave model, the probability of finding an electron within a certain volume of space surrounding the nucleus can be represented as a fuzzy cloud. This cloud is more dense where the probability of finding an electron is high. So this fuzzy cloud corresponds to atomic orbital. An atomic orbital is often thought of as a region of space in which there is a high probability of finding an electron. And instead of using a cloud, we usually let it be represented with something with a sphere or some other shape, where it's the region of space for 90% probability of finding an electron. So instead of looking at this cloud, we usually give a definite shape and say that 90% of the time we will find the electron somewhere in it. So if you were to look at a hydrogen atom and record the location of everywhere you found an electron, you'll eventually get this orbital shape. The probability cloud of locations you found the electron. It's very messy. You can see that it's more likely to be in the center, but we usually replace it with a sphere and call it the atomic orbital. Thus, 90% of the time, we find the electron in it. These orbitals are going to be on the next test, and not this test. I can tell you right now, this test is going to only deal with isotopes and the history. Because orbitals get somewhat advanced, I'm grouping all the orbitals in just one test by itself. So you don't have to memorize the history, you can really get down the orbitals. So to just go over the orbitals real quick, we'll go back over it for the next test. So s orbitals are spherical, p orbitals are dumbbell shaped. There are 3 types because we live in a 3D universe. When they all combine together, and then we have d orbitals and f orbitals. And the rest of this is going to be all for when we cover other orbitals in more detail. Why atoms are spherical is whenever you pack all these orbitals together, you get a somewhat spherical shape. So let's look at atoms and isotopes. So atoms contain protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. The nucleus contains most of the mass of an atom. Electrons are distributed around the nucleus in energy level, shells, and orbitals. So in the Bohr model, the circles represent energy levels. There can only be 2 electrons in an orbital, but there can be certain number of electrons in each energy level. So the innermost energy level has at most 2. The second energy level has, I think, 6 at most. We'll learn that later, though, when we get more into detail in orbital. But usually the Bohr model is just energy level shown. So the outermost electrons in the shell are going to be called the valence electrons. All of chemistry mostly just deals with valence electrons. When we go over this, we'll see that learning about valence electrons is very, very important. Almost everything about atom has to deal with this valence electron, which is just the electrons in the outermost shell. Which I think shell in this case means energy level. I need to look up to confirm that. No, it would be shell. Yeah, I think there's a distinction between them. Right now, it's not important to know the difference between energy level shell. So, electrons, first subatomic particle discovered by J.J. Thomson using a cathode ray tube. Cathode ray tube is a tube filled with gas of one element that allows you to run electricity through it. So it has a terminal that runs through the glass, so a metal cap on one side and a wire tube running through the glass on the other that allows you to run electricity to it. The charge of an electron is -1. Electrical units, we just usually say it's -1. This is a negative charge. The mass is 9.11 times 10 to the -28 grams, or an AMU unit 0.0005. The atomic mass unit. So the mass of the electron is negligible. You can almost treat when you're talking about the mass of an atom, you can basically ignore the electrons and you don't really add any weight to it. Electrons are located at energy levels which make up the electron cloud. Electrons in the outermost energy level are called valence electrons. I would memorize that other shell. The outermost energy level is the valence electron. Valence electrons are responsible for the reactivity of the atom. So whether or not it will react with another atom only has to do with the valence electrons. So proton was observed by Goldstein in 1896. Though Rutherford is given credit for showing that atoms contain both negative and positively charged particles. So Rutherford is given the credit. I don't think I have Goldstein on the test. I think it's Rutherford. Protons have a charge of +1 and a relative mass of 1 AMU. So a proton has one atomic mass unit. Electron is 0.0005. So there's a huge gap between the mass of an electron versus the mass of the proton. If you were to write in grams, that's 1.673 times 10 to the -24 grams. The third major subatomic particle was discovered by James Chadwick. It has no charge, so it's neutral, and has a relative mass of about 1 AMU. If you look at it in grams, you'll see it's ever so slightly larger in mass than a proton, 1.675 instead of 73. So what is an isotope? Atoms of the same element have the same atomic number, the number of a proton. So every gold atom, or every carbon atom, has 6 protons. What determines the type of atom is the number of protons. That is the only thing that tells you what atom it is. You count the number of protons, that tells you the atom. So every single carbon atom has 6 protons. Every hydrogen atom has 1 proton. Every oxygen atom has 8. What determines the type of atom is the number of protons. And so every atom that has the same number of protons has very, very identical chemical properties. There might be some small changes due to mass because it's heavier, but basically it's almost entirely the exact same. However, atoms of the same element may have different number of neutrons and thus have a different atomic mass. So isotopes are atoms of the same element that have different number of neutrons. I highly recommend writing this down. So this is how we write elements. We have a symbol. So the element symbol, here is just an X right now. On the top left, we have the mass number. Mass number is equal to the number of protons plus the number of neutrons. And then on the bottom left, we have something called the atomic number. The atomic number is going to be the number of protons. This is how we write atoms down when we're referring to a specific type of atom, especially when we're talking about different isotopes. Often you'll see the atomic number left off because if you know it's carbon, you know all carbon atoms have six protons. So it's kind of redundant to put both the atomic number and the element symbol. By the way, on the periodic table, these letters are not called letters. They're called symbols. We just happen to use the same symbols that we use in Latin alphabet. You could have technically gone in and made every one of these circles with dots, crosses, a picture of a heart on one. It would be very hard for us to read, but they actually used to do that. If you actually, when we didn't know how many, when we didn't discover the when we didn't know about all the atoms, and elements and stuff, we had hydrogen with a circle with a dot, iron with a circle with an eye, zinc. Note that we also thought these were elements. Sulfur was this. So we still keep up and call these symbols. We just changed all the symbols to match our Latin alphabet. So for example, krypton has a mass number of 94 and has an atomic number of 36. So 36 tells us it has 36 protons, and that's also krypton. 94 is the number of protons plus the number of neutrons. So if we wanted to calculate how many neutrons were in this isotope, we just subtract the two numbers. 94 minus 36 gives you the number of neutrons. So let's look at hydrogen. Every element has naturally occurring isotopes. Hydrogen has 3 naturally occurring isotopes. Their names are protium. It's the most abundant isotope. It has 1 proton, 0 neutrons, and 1 electron. Deuterium has 1 proton, 1 neutron, and 1 electron. Tritium has 1 proton, 2 neutrons, and 1 electron. So almost every hydrogen atom, 99.985% of them, has no neutrons and 1 proton and electron. Again, isotopes only differ by the amount of neutrons they have. The second, if you knew your Greek, DEUT is 2, and tri as in a triangle is 3. Pro is also your base or 1. Which is referring to the mass numbers in this. So the mass number for deuterium is 2 because it has a proton and a neutron. Tritium has 1 proton and 2 neutrons, so its mass number is 3. So we look at these 3. protium, deuterium, and tritium. Isotopes can be radioactive and unstable. Unstable just means they're radioactive. If it's not stable, eventually they will break apart, the nucleus will disintegrate. That's how we get radiation. Tritium is radioactive. Deuterium, I think, is slightly radioactive too. I forget the half-life on that. It's not important right now. So we have this notation to write isotopes. We also have another notation. It's the hyphen name notation. So let's look at chlorine, what has a mass number of 35 and an atomic number of 17. And we have chlorine 37 that has a mass number of 37 and an atomic number of 17. So the symbol notation is up above, and the hyphen notation is down below. The hyphen notation is just the name of the element, hyphen, and the mass number. Other than hydrogen, almost every element's name is just usually going to be this hyphen notation. Hydrogen has unique names for the 3 different isotopes. No other isotope has that. You probably already heard of one common isotope, carbon-12, carbon-13, or carbon-14. So you probably heard of carbon dating. Carbon dating uses carbon-13, I believe, because it's slightly radioactive. So naturally occurring carbon is this 3 isotopes: carbon-12, carbon-13, and carbon-14. So state the number of protons, neutrons, and electrons in each of these. So how many protons do they all have? 6. So again, the bottom left number is the number of protons. Since this is all carbon, we also know it's 6. And usually, so we don't see a minus or a positive sign anywhere near this. So that means they're all neutral. Neutral means that they have the same amount of positive charge as they do negative charge. The number of electrons will be the same as the number of protons. So they all have 6 electrons. Again, the only way isotopes differ is by the number of neutrons. So to find the number of neutrons, we take the mass number and subtract the atomic number. So for the first one, it's 12 minus 6, so it has 6 neutrons. For carbon-13, it's 13 minus 6, so it has 7 neutrons. And for carbon-14, it has 14 minus 6, so 8 neutrons. So an atom of zinc has a mass number of 65. By the way, from this point onward, y'all will most definitely be needing y'all's periodic table almost every day. So an atom of zinc has a mass number of 65. What is the number of protons in a zinc atom? So looking at the periodic table, this number is number 30. So that corresponds to 30 protons. If it has 30 protons, what would be the number of neutrons? So remember, number of neutrons will be equal to the mass number minus the number of protons. So 65 minus 30. So it has 35 neutrons. What will be the mass number of a zinc isotope with 37? So mass number is just number of protons plus number of neutrons. So 30 protons plus 37 neutrons gives you 67. So the mass number of zinc isotope with 37 neutrons would be 67. We'll look more in detail about atomic mass tomorrow. I think are we out of time? Yeah, we'll do it tomorrow.